Here is our numerical example, and we have advertising, right, and sales. Okay, so we can prepare a scatter plot of this. Okay, sales, and this is advertising. How much are we spending on advertising? So we'll take that out. So and then we have sales. So that is, you can see there is a relationship, but that's kind of up and down. And this relationship is what we want to simulate. And but before we get to simulation, we want to run a deterministic model. So without parameter uncertainty. So Excel has in data analysis, we have what is called regression here, and if you select that, and then Y range is sales, X range is advertising. So we have included the labels for the columns, so we have to check that. Okay, and then let's say we want to put the output in this sheet here. Okay, so now click OK, and we have the output. All right, so here these are the coefficients, and here are the degrees of freedoms. Okay, and we have the sum of squares. So this is your sum of squares of regression. This residual is another name for error. So that's your SSE. Then MSR is you divide the degrees of freedom into the sum of squares, you get the mean square. So you find the ratio of MSR and MSE, you get what is called F, and this is the p-value. We'll talk about that in just a second. And each of these coefficients also come with standard error. So that tells us the variability inherent in the coefficients, because these coefficients are based on our sample data. What if the sample data is different? So your coefficient is going to be different. So the amount of variability associated with our estimates of these coefficients is indicated here. And this standard error right here is the square root of this MSE. MSE, these are related. So this is square root of that. Okay. So now let's go to Word document and then see what the inference about this. See, these unknown parameters, beta sub 0 and beta sub 1, is what we wanted to estimate, and that's how we came up with this b sub 0 and b sub 1 values. So if b sub 0 and b sub 1 are our estimates based on a single sample, a different sample will give you different estimates. So we have the standard error. Now dividing the coefficient by the standard error follows a student t distribution. So let's put this on our Excel side by side. Okay. So here if you take the coefficient and divide by the standard error, we get the t statistic. So that's what this statement says. And then based on that t distribution, we can come up with p-value. P-value tells us whether the coefficient is 0 or not. Okay, so let's change this to percentage. So, all right. So p-value is the probability that we are making a wrong conclusion if we decide that the unknown parameters beta sub 0 and beta sub, so that should be beta sub 0 and beta sub 1 or 0. So we are starting out saying, all right, so we think that there is a relationship and it goes like that, but maybe there is nothing. Maybe it is just flat like that. So flat like that come down here. So beta 1 is 0, beta sub 0 is 0, so it's all zeros anyway, so nothing there. Then that's one possible. Or we can say, no. There is a relationship. It is not flat. Okay. It is not flat. And it is not 0. The intercept is not 0. Okay. If we say that, okay, what is the probability that we're going to be wrong? If we say, no, it is not 0, then the probability that we are wrong, okay, is given by that. Okay, so it looks like it's close to 0. So our intercept is being 0. If we say, okay, intercept is not 0, then the probability that we're going to be wrong is 82%. Well, that should give you a pause. Now, if you say that the slope is not 0, okay, then your wrong is only 0.01%. So you can, since 0.01% is so small that we can confidently say that the slope is not 0. It is something different from 0. So that's what the p-value is, and as an alternative to p-value, you have confidence intervals. So we will not get into that. So if this is what going to be our basis, then we can go ahead and set up forecasts for that. Okay. So let's say that that's the advertisement, and okay, so sales data, right? All right, no. The forecast based on regression is going to be, so we can actually use the regression coefficients from here. Okay, so the intercept and advertising is your slope coefficient. We can put that here, or we can use a function. So we need to use the function because when we start simulating, we want these intercepts to be automatically recalculated, which will not be the case in the regression output. So we need to really use the function. So y values and the x values will give you the intercept, and then we have a function called slope. Again, y values, x values, okay, and then the standard error of y given x, again there is a function for that, that is std ste yx, a standard error of y given x. So again, y values and x values. All right, let's set that up. Okay, so now if you want, we can set up the forecast based on this for each of the existing advertising values. So we can say, all right, so that's your intercept, and let's absolute reference that, plus there is our x value, okay, times slope. Again, absolute reference that. So that gives us the deterministic forecast without any simulation. Now we have the estimate, okay, for the existing values, advertising 1 through 10. But suppose we want for 7,500, these are supposed to be in thousands. So suppose we set a budget of 7.5 or 7,500 for X. Okay, so now what is our forecast for sales? Okay, and again, okay, so that is intercept plus slope times that. So that will give us the forecast. But of course, this is based on one sample and one estimate based on that sample. So our reliability of this is quite low. Now we want to be able to simulate and get a more robust set of estimates for the intercept and slope. So we are going to incorporate what we already looked at in a previous example, parameter uncertainty. So these parameters are uncertain. So how do you incorporate the uncertainties? And like what we did previously, we will do bootstraps, like we will simulate, we will sample from the existing samples more samples and then try to fit new regression estimates from the bootstrapped sample.